So all of you, welcome to the session. Today we are going to derive an equation that is what? Cp by Cv equal to gamma, that equal to Es by Et. So this one we are going to derive today. Let us see what it means. The ratio between specific heat of specific heat capacities of substance at constant pressure and constant volume is equal to the ratio between adiabatic elasticity and isothermal elasticity. Okay, the ratio between specific heat capacities of substance at constant pressure and constant volume is equal to ratio between adiabatic elasticity and the isothermal elasticity. So now let us see how can we derive this equation. Okay, so you have to remember this one. For this, we know that elasticity can be written as E equal to stress by strain. So we know that stress can also be written as pressure in terms of pressure, dP by strain. So dV, change in volume by actual value. So what minus represents? Where minus represents when the pressure is applied on the substance whose value can be decreased. So P equal to, so he will write minus V into dP by dV. So let us assume this is equation number 1. So this is generally elasticity equation, E equal to minus V dP by dV, right? So now elasticity in adiabatic process. How can we write elasticity in adiabatic process? Which one is constant in adiabatic process? Yes, tell me which one is constant in adiabatic process. Entropy is constant. That is why we will write Es is equal minus V into, so dP by dV into, here it is, S is constant. And similarly, elasticity in isothermal process, so that is where the temperature is constant, so Et equal to minus V, and we will write dP by dV at a constant temperature. Okay, now divide these two equations. Let us take here, let us write Es by Et. Right, Es by Et. So what we get there? Es by Et equal to, so minus V get cancelled, and finally we have term dP by dV at a constant entropy by, here we will write the dP by dV at constant temperature. Okay, so this can also be written as dP by dt, just divide and multiplication. Here I am writing this one as, instead of taking dP by dV, I am going to write there dou, right, partial differentiation. So dou P by dou T into dou T by dou V. Okay, here you have to write S, and here you have to write S, and similarly by. So what we get there? So here we have to write this one as the dou T by dou S and the dou S by dou V. Here you have to write constant temperature. Here we have to write constant temperature. Okay. So with the help of Maxwell 4 equations, Maxwell thermodynamic equation 1, 2, 3, 4, by using that 4 equations, we have to change these bracket terms. Okay. So anyway, so let us take first one here. What is that? Dou P by dou T. Here it is constant entropy. I am writing this one, as see there carefully. This can also be written as 1 by, so dou T by dou P, right? Dou T by dou P. Here it is constant entropy. According to Maxwell's law, so this can be written as 1 by, so 1 by, here I am writing, so dou V, okay, dou V by dou S. Here it is what? Constant pressure. And again we are adjusting this one, what we get there? So according to Maxwell's equation, dou T by dou P at constant entropy can be written as dou V by dou S constant pressure. So again, this one written as, so dou S by dou V at a constant pressure. Okay, so let us assume this is what equation number 2, and this is what equation number 3, and this is 4, and this is what equation number 5. And similarly here, and the second term, this one, so dou T by dou V at constant entropy, so can be written as, so we know very well, that is what directly minus dou P by dou S at a constant value. Assume this is equation number 6. Okay, and similarly from this one, this term dou P by dou S, right, dou P by dou S at a constant temperature can also be written as 1 by, so dou S by dou P T, and according to Maxwell's equation, this can be written as 1 by, here we write dou P by dou T. So here dou V by dou T, okay, at a constant pressure. So this can again will be written as dou T by dou V at a constant pressure. So this is what equation number 7. Okay. Again dou S by dou V. So here we have minus, we get the minus, here also minus will get there. Okay. So from and the fourth term dou S by dou V, we know that directly we can write dou S by dou V. Dou S by dou V T equal to dou S by dou V, T equal to, directly we can write this one as dou P by dou T at a constant value. So this is what equation number 8, and the substitute equation number 5, 6, 7 and 8 in equation number 4. So let us see what happened after substituting all the terms in equation number 4. Okay, so what we get there, if we substitute all these 4 equations in equation number 4, we'll get there ES by ET equal to, in place of dou P by dou TS can be written as dou S by dou V at constant pressure, dou S by dou V at constant pressure, into, what about this one, dou T by dou V? Dou T by dou V can be written as dou P by dou S at a constant volume, right, at a constant volume. Here we get there minus by, and this term, what is that term, represents dou P by dou S at constant temperature, can be written as minus dou T by dou V at the constant pressure P. And the fourth one is, we know that dou P by dou T at a constant value T. Okay, so from these equations we know that where here pressure is constant, here pressure is constant, and dou V get cancelled, and finally we have the term ES by ET equal to we'll get there dou S by dou T at constant, dou V cancel, and we'll get the dou S by dou T at a constant pressure P, where minus get cancelled, and but into here, and we have to write here dou P and dou P get cancelled, here this one cancel, and finally we have the term, what we get there, dou S by dou T, right? Dou S by dou T, here we get there dou S by dou T, okay, at a constant value, right? So we got this one, and now what we have to do, we have to multiply with T. Multiply and divide with T. So what we get there, ES by ET equal to T into dou S by dou T, constant pressure, by T into dou S by dou T at a constant value. Okay, so now we can write here T dou S can be written as dou Q. Okay, substituting in the above equation, we get there ES by ET equal to, what we get there, dou Q by dou T P, and dou Q by dou T at constant value V. This can also be written as Cp by Cv. Okay, so finally we got that the ratio between the adiabatic and isothermal elasticities are equal to the ratio between specific heats at the constant pressure and the constant values. So Cp by Cv, that is equal to gamma. So this is what our required equation, ES by ET equal to Cp by Cv equal to gamma.
It relates, but the Clausius-Clapeyron equation relates
The change in boiling point or melting point with change in pressure. See that? But the Clausius-Clapeyron equation relates the change in boiling point or melting point with change in pressure. Okay, let us see how the pressure is related to the boiling point and melting point with the help of one equation. Okay, with the help of one equation. Now, so according to Maxwell's second law, from Maxwell's second thermodynamic equation, Maxwell's second thermodynamic equation, dou P by dou T at constant volume V is equal to, dou P by dou T at constant volume V is equal to dou S by dou V at a constant temperature. So we know very well about this equation. Okay, now multiply with the T on both sides. What we get there, T into, so dou P by dou T V, that equal to T into dou S by dou V T. So we know that where T dou S can be written as dou Q. Okay, substituting the equation, then finally what we get there, T into, so dou P by dou T at constant volume is equal to, so dou Q by dou V, okay, dou Q by dou V at a constant temperature. at constant temperature. You have to remember this equation. You have to remember this equation. Now, let us take 1 unit mass substance. Let us take one unit mass substance. 1 unit mass substance. Okay. I'm taking 1 unit mass substance which is changing its state from one, it is changing, that substance is converting from that substance, the state of the substance is converting from one state to another state. Okay, the state of the substance is converting from one state to another state by observing some heat at a constant temperature. Okay, understand what is happening? I'm taking 1 unit mass substance. Okay, now what happened here? The state of the substance is converting from one state to the another state by observing some heat at a constant temperature. That heat may be taken as latent heat. That heat can be taken as latent heat. Okay, so for this, what happened here? 1 unit mass, and how much energy it is receiving, how much heat energy is receiving, dq heat energy, that is in the form of latent heat. So where we can write, if the state of the system is changing from one state to another state, that means whose volume also changing. So therefore here dou q can be written as here ml, but m is equal to 1 unit, so we can write only L, latent heat. So latent heat. Okay, now the volume can be taken as dou V equal to V2 minus V1. Substitute these two terms in above equation. Let us see what we get. What we get there finally? We'll get there T and dou P by dou T at a constant volume V equal to, we'll get there L by V2 minus V1. So from this one we'll get there dou P by dou T at a constant volume. Otherwise we can write dou P by dou T equal to L by T into V2 minus V1. So this is the equation of Clausius-Clapeyron's equation. Clausius-Clapeyron's equation, dou P by dou T equal to L by T into V2 minus V1, where L is latent heat, where the T is absolute temperature, and where V2 minus V1 is nothing but change in volume. Dou P by dou T equal to L by T into V2 minus V1. Clausius-Clapeyron's equation according to Maxwell's second thermodynamic equation. Okay. So let us see few applications of Clausius-Clapeyron equation. First one, explanation of effect of pressure on melting point of solids. See, we know that just now we got equation Clausius-Clapeyron's equation, that is what dou P by dou T equal to L by T into V2 minus V1, where V1 and V2 are the specific volumes of the substance at the solid and liquid phase, and dP is the increase in pressure. Let us see here. In case of melting point of wax, we know that wax, right? Candles are prepared by wax. Okay. So in case of melting point of wax, V2 minus V1 is positive. You know that when the candle melts, the volume of candle is less than the melted wax. Okay. Now what happened? V2 minus V1 is positive here. Okay. Since L and T are necessarily positive, because latent heat and the temperature are necessarily positive, dP by dt is positive. That is, melting point increases with increase in pressure. Okay, melting point increases with the increase in pressure. You have to remember that point. Okay, but whereas in case of other materials, what happened? Let us see. In case of melting point of ice, if you take ice, so when it melts, it become water, then the volume of the water is less than the volume of the ice. Therefore, what happened? V2 minus V1 is negative. Yes, V2 minus V1 is negative. Since L and T are positive, what happened? dP by dt is negative because V2 minus V1 is negative. That is, melting point is lowered with the increase in pressure. You have to concentrate here. What is happening here? Melting point, where the melting point is lowered with increase in pressure. With increase in pressure. Right. So this is what so happen during the melting points of solids. Now let us see effect of pressure on boiling point of a liquid. You know that boiling point of a liquid. Let us say in case of evaporation, V2 is greater than V1. We know it is very obvious that volume of the gas is greater than the volume of the liquid. So what happened there? V2 greater than V1, that is V2 minus V1 is positive. Since L and T are positive, dP by dt is positive, that is boiling point of any liquid rises with increase of pressure. So for example, if we take pressure cooker, what is the principle behind the pressure cooker? So what is so happening inside the pressure cooker? See there, the boiling point, that means evaporation of liquid point is rises with increase of pressure. As a result, what happened? The temperature of the liquid is more than the whatever the vegetables, rice cooking inside the pressure cooker is it's take less time to cook the food. Okay, because of it's a boiling point of the liquid increases and the temperature of the liquid increases. As a result, what are the materials we took in the cooker, they cooked in the lesser time. Okay, so this is this principle lies in the pressure cooker. So here in case of evaporation, V2 greater than V1, that is V2 minus V1 is positive. Since L and T are positive, dP by dt is positive, that is boiling point of any liquid rises with increase of pressure. So you know that one thing is, when we go hill areas, when we cook the rice on the normal stove, what happen? It takes more time. What happen? There is that the pressure is very less. Due to the less pressure, what happen? It takes more time, and whose boiling point is less, the boiling point of water is less on the hill areas. What happened? Without cooking the food properly, all the water is evaporated. So therefore, the rice is not cooked properly on the hill areas. But if you take the pressure cooker, on the hill areas, it is very easy. What happened? With the help of pressure cooker, we are increasing the pressure. As a result, the boiling point, that means evaporation point of water also increases. So in that case, what happened? We can cook the rice properly. Okay. And next thing is, this is the wonderful example. If you take two ice pieces and we have to put together and just apply the force from both sides, so what happened? After certain time, that two ice pieces become single piece. Why it is so happening there? Let us see here. The phenomenon of melting of ice under pressure and refreezing on release of pressure is called resolution. You know that if you take two pieces together and applying the force with the thumb and index finger on sides of that two pieces, when we are applying force, that means indirectly we are applying the pressure on the ice cubes. So after a certain time, it will become single piece. Why? Because see that the phenomenon of melting of ice under pressure and refreezing on release of pressure is called resolution. See there, what is so happening inside that? Ice contracts on melting. Hence, V2 minus V1 is negative. We know that when the ice melts, it will become water. Then the volume of the water is lesser than the volume of the ice. Therefore, V2 minus V1 is negative. Since dP by dt is negative, melting point of ice is lowered. See there? Since dP by dt is negative, the melting point of ice is lowered with increase in pressure. Then what happens? Thus, when two ice pieces are pressed together, the melting point is lowered so that some ice melts and a thin film of water is formed. Between the surfaces of in the contact.
On the removal of pressure, the original melting point is replaced, hence water is frozen, thereby the two ice pieces stick together to form a single block. So it is a wonderful example. You just take two ice pieces from your refrigerator and put them together and just apply the forces from two sides, then immediately you can observe this result, resolution. That is what we call resolution. Okay, so these are the examples of applications of Clausius-Clapeyron's equation. Okay.